Some ancient structures stand so perfectly engineered that modern engineers still cannot explain how they were built. Stay to the end of this journey to uncover 10 infrastructure mysteries from the medieval and earlier worlds that continue to puzzle researchers, from Roman concrete that lasts 2,000 years to Inca stones cut with impossible precision. How did builders raise soaring cathedral vaults without modern safety calculations? How did underground cities provide fresh air and water for thousands of people? Each mystery reveals a lost technique, a forgotten skill, or a gap in the historical record that turns our assumptions upside down. Do you think the greatest achievements of the past are still ahead of us? Or have we already lost something essential? From harbor piers that have stood for nearly 2,000 years to the unreinforced dome of the Pantheon, Roman concrete remains the gold standard of ancient durability. Modern concrete often begins to crack within decades, yet these Roman structures still stand, some even in direct contact with harsh seawater. Researchers have long debated what gave this material such remarkable longevity, and the answer may be more complex than a single ingredient. The key ingredient was volcanic ash, known as pozzolana, which Romans sourced from the region around Vesuvius and other volcanic areas. When mixed with lime and water, this ash created a chemical reaction that formed crystals so strong they could bind together rock fragments into a nearly monolithic mass. But recent studies suggest that the mixing process itself may have been just as important. Evidence indicates that Romans often used hot lime, meaning the lime was not fully slaked before being mixed with the ash and aggregate. This hot mixing process generated intense heat, which caused microscopic cracks that later filled with growing crystals, strengthening the concrete over time rather than weakening it. This self-healing property is something modern concrete lacks entirely. Engineers have tried to recreate Roman concrete using the same materials, but the results are inconsistent. The quality of the volcanic ash varied from quarry to quarry, and the exact proportions used by Roman builders remain unknown. Some experiments have produced durable concrete, but none have matched the long-term performance of ancient samples. This gap in knowledge frustrates researchers because if we could fully understand the process, we might build infrastructure that lasts for millennia, reducing waste and maintenance costs dramatically. Yet the mystery runs deeper than just chemistry. Roman writers like Vitruvius described concrete recipes, but their accounts are often vague or contradictory. Were there trade secrets passed down within guilds that never made it into written record? Did local variations in materials force builders to adapt techniques that were never standardized? The more we study these ancient structures, the more we realize that Roman concrete was not a single formula but a living tradition, refined over centuries through trial and error. That kind of embodied knowledge is almost impossible to recover from texts alone. What might we learn if we could travel back in time and watch a Roman engineer at work? The answer may lie hidden inside those enduring walls, waiting for the right combination of science and observation to bring it back to light. No list of ancient infrastructure mysteries is complete without the roads that stretched across an entire empire. Roman roads like the Via Appia were engineered with such straightness that long sections deviate less than a few degrees over many miles, even when cutting through hills, valleys, and marshes. Modern surveyors would need laser rangefinders and satellite coordinates to match that precision, yet Roman builders achieved it using tools that look almost primitive. The primary instrument was the groma, a simple vertical pole with 4 horizontal arms and dangling plumb lines. By sighting along 2 lines at a time, a surveyor could mark a straight line between 2 points. But the groma had major limitations. It required a clear line of sight and a calm day, and it was notoriously inaccurate over long distances because even a tiny error at the start multiplied as the line extended. How then did Roman surveyors maintain alignment for dozens of miles? Some researchers suggest they used a technique called back-sighting, where they set up multiple gromas behind one another and adjusted each by looking back at the previous mark. Others propose that they used the sun or stars as fixed reference points, a practice described by Roman writers like Frontinus, but written records are frustratingly vague. The manuals that survive describe the tools but not the step-by-step procedures for long-distance alignment. Another mystery is how they handled terrain that blocked direct sight. For example, the Via Appia cuts straight through the Pontine marshes, a swampy lowland where a surveyor could not stand in the middle to take a reading. Some archaeologists believe the Romans built temporary observation towers to raise the groma above obstacles. Others think they used a method called triangulation, setting up a network of right angles to project the line forward around a hill. Without either scenario being proven, the debate continues. What makes this uncertainty so striking is that the roads themselves survive as evidence of the skill. The Via Appia still runs in a straight line from Rome to Brindisi, nearly 400 miles, with sections that are arrow straight for 10 or 15 miles at a time. Modern attempts to replicate this feat using period tools have had mixed results, often producing alignments that wander far more than the originals. This suggests that the Romans possessed a surveying mastery that went beyond the tools themselves. Perhaps it was an accumulated craft passed down through generations of surveyors, with tricks for reading the landscape that never made it into textbooks. Or maybe they used a combination of methods we have not yet reconstructed. Whatever the answer, the roads remain a silent challenge to our assumptions about ancient engineering. If we cannot fully explain how they laid out such perfect lines, what other lost skills might be hidden in the everyday structures we take for granted? From straight roads to vaulted heavens, the next mystery soars even higher. Gothic cathedrals like Chartres and Beauvais still inspire awe not only for their beauty but for the sheer audacity of their engineering. Builders raised stone ceilings over 120 feet above the floor, thin as eggshells, supported by pillars that seem impossibly slender. Modern structural engineers have run computer models on these buildings and discovered something unsettling. Some of the vaults operate at the very edge of their theoretical load capacity. A single miscalculation could have brought the entire roof crashing down, yet they have stood for over 800 years. How did medieval builders know they had pushed the limits safely? The traditional answer points to two innovations: ribbed vaults and flying buttresses. Ribbed vaults replaced heavy barrel vaults with a framework of diagonal stone arches, concentrating weight onto specific points. Flying buttresses transferred that weight outward and down to massive piers away from the walls, allowing for taller windows and thinner walls. But this explanation only covers what they did, not how they knew it would work. The debate among historians and engineers centers on whether these builders used any form of structural analysis or relied entirely on empirical trial and error. Cathedrals like Beauvais, whose vault reached over 150 feet, collapsed partly during construction in the 13th century and had to be reinforced. That collapse suggests that some attempts exceeded the limits of available knowledge. Yet even Beauvais, after rebuilding, stands today as a lesson in what happens when ambition outpaces understanding. At Chartres, which never collapsed, the proportions are so finely tuned that engineers have calculated safety margins of less than 10% in some sections. In modern construction, a safety margin of 300% is considered standard. How did the Chartres builders land so close to the boundary without crossing it? Some researchers suggest they used geometric rules of thumb passed down through guilds, rules that encoded centuries of experience into simple ratios. Others point to the physical models they may have built, full-scale wooden templates called centering, which held the stones in place while the mortar cured. Perhaps they gradually adjusted the shape and thickness based on how earlier structures behaved, but written records from the period are almost entirely silent on engineering calculations. Stonemasons kept their knowledge secret, and what little was written is practical rather than theoretical. This means we may never know exactly how they determined that a 40-foot rib could support 100 tons of stone. The mystery is not merely academic. Modern engineers trying to restore these cathedrals face the same question. If you replace a worn stone, you alter the distribution of forces. Without understanding the original logic, you risk triggering a collapse. So the cathedrals themselves hold answers we still struggle to read. Perhaps the greatest discovery would not be a formula, but an appreciation for how deeply master builders understood the behavior of stone through touch, observation, and memory. What other forms of knowing have we lost in our age of calculators and computer simulations? At the Alhambra in Granada, water flows as if by magic. Fountains rise and fall in precise patterns. Baths fill to exactly the right depth, and garden channels run cool and clear even during the driest summer months. Yet this entire system was built over 600 years ago without electric pumps, without modern plumbing, and without any written manuals that fully explain how it worked. The engineering mystery at the heart of the Alhambra is not whether they moved water, but how they lifted it to the palace heights and maintained constant pressure across such a sprawling hilltop complex. The source was the Darro River, which runs through the valley below. From there, a network of gravity-fed channels called acequias carried water along the contours of the mountainside, sometimes tunneling through rock, sometimes running along the surface in open stone channels. These acequias were common throughout Islamic Spain and represented a sophisticated understanding of hydraulics, using the natural slope to keep water moving at a steady pace without eroding the channel walls. But the Alhambra sits atop a plateau nearly 200 feet above the river. Gravity alone could not push water uphill. Something had to raise it. The traditional explanation points to a large water wheel known as a noria installed near the riverbank. This wheel, turned by the current, would lift water into a raised aqueduct that then fed into the palace system. Remains of such a wheel have been found, but its exact design and capacity remain debated. Could a single noria provide enough water for the Alhambra's 12 fountains, multiple bathhouses, and extensive gardens? Some researchers argue that the wheel was supplemented by a series of smaller wheels or even a chain pump, a device where a loop of buckets scooped water continuously. Others propose that siphons played a role, using the principle of air pressure to carry water over a low ridge. Siphons were known to Roman engineers, but evidence for their use in Islamic Spain is sparse. The mystery deepens when you consider the precise control of water pressure. The Alhambra's most famous fountain, the one in the Court of the Lions, operates with 12 jets that rise to the same height, perfectly balanced. Achieving that balance in a gravity-fed system requires careful regulation of pipe diameters and elevation differences. Modern engineers who have modeled the system find that even small changes in the slope or pipe size would disrupt the symmetry. So the builders must have understood fluid dynamics at a level that seems almost intuitive, yet no written records from the Nasrid dynasty describe these calculations. The knowledge was likely passed orally among the hydraulic engineers, a specialized guild whose techniques vanished with the fall of Granada in 1492. What makes this loss so frustrating is that the system still works after all these centuries with only minor restoration. The original ceramic pipes, some only 4 inches wide, still carry water to the same fountains. They were laid with such precision that they rarely clog despite the mineral-rich water. When archaeologists recently excavated sections of the underground channel network, they found stone filters designed to catch sediment, carefully placed at strategic junctions. These filters were cleaned through small access holes, maintenance features later builders forgot to include in their restorations. So the Alhambra stands as a living laboratory, a working water system whose designers left behind no instruction manual. Every time a fountain sprays into the air, it is a question that remains unanswered. How did they lift the water, control its flow, and maintain it so well that we are still trying to reverse engineer their methods? The answer, if it is ever found, might transform how we design sustainable water systems in arid regions today. From the flowing fountains of the Alhambra, the next mystery descends deep into the earth. Beneath the soft volcanic landscape of Cappadocia in central Turkey lies the underground city of Derinkuyu, an entire world carved downward through multiple levels, reaching depths of nearly 200 feet. Archaeologists have uncovered at least 18 separate subterranean cities in this region, with Derinkuyu being the largest that has been open to the public. This sprawling network could have housed 20,000 people, complete with living quarters, food storage, stables, schools, and even a chapel. The first question that puzzles researchers is who built it and when. The soft, tough rock is easy to carve, but the sheer volume of excavation is staggering. Removing millions of cubic feet of rock by hand, using only iron chisels and hammers, would have taken generations. Some historians argue that the earliest levels date back to the Hittites around 1200 years before the Common Era, while others point to the Phrygians or later Persian influences. But the most intriguing evidence points to the medieval period. During the Byzantine era, around the 7th through 12th centuries, local Christian communities expanded the city to protect themselves from periodic conflicts. They carved new tunnels, deepened existing chambers, and created a system that could sustain life underground for months at a time. This medieval expansion is what creates the greatest engineering mystery. How did they solve the problems of ventilation, lighting, and fresh water in a space with no windows and minimal access to the surface? The ventilation system alone is a marvel. Vertical shafts were carved through the rock from the top level to the bottom, drawing fresh air downward and allowing stale air to rise. These shafts also served as wells, and some researchers estimate that the airflow was strong enough to keep torches burning and people breathing even at the deepest levels. Yet the shafts are narrow, only a few feet wide, and black with soot from centuries of use. Modern engineers have run computer simulations showing that the system works surprisingly well, but only if the shafts are clear and the passages are sealed correctly. That suggests a sophisticated understanding of air pressure and chimney effect. Lighting was another challenge. Torches and oil lamps would have consumed oxygen and produced smoke. The inhabitants likely relied on multiple small lamps placed in niches along the corridors, and the smoke would have risen to the ventilation shafts. But the heat from those lamps would have affected airflow, creating a delicate balance that had to be maintained. The water supply is equally impressive. Deep wells tapped into the groundwater table, but those wells had to be dug from the surface downward, and they had to align with the underground levels. Some of these wells are nearly 300 feet deep, and they are still functional today. The inhabitants also built large cisterns to collect rainwater that seeped through the porous rock. These cisterns were lined with waterproof plaster, and they provided enough water for the entire population. But the storage capacity raises another question. How did they keep the water fresh for months without modern filtration? The answer may lie in the rock itself. The volcanic tuff is rich in minerals that naturally purify water as it slowly seeps through. The inhabitants likely understood this property and designed their cisterns to take advantage of it. So Derinkuyu was not just a refuge, it was a fully self-sustaining habitat built with a level of foresight that seems almost impossible for a medieval community. Why go through such immense effort? The debate over purpose continues. Some historians argue that these cities were built as a permanent retreat, a place to live year-round in times of peace, while others see them as emergency shelters used only during raids. The presence of churches, schools, and wine presses suggests long-term habitation. Yet the narrow corridors, low ceilings, and tight quarters make daily life feel cramped and uncomfortable. Perhaps they were used seasonally for harvest storage and periodic gatherings, or perhaps the builders intended them as a final sanctuary, a place where a community could survive even if the world above was destroyed. The mystery remains because the inhabitants left no written records explaining their choices. Everything we know about Derinkuyu comes from the stones themselves, from the wear marks on the floors, the soot on the ceilings, the grindstones left behind. Researchers continue to explore new chambers with ground-penetrating radar, and every year they discover more tunnels and rooms that were previously unknown. The full extent of the underground city may still be hidden. What drove people to carve an entire civilization into the darkness? And what would it feel like to live for months without seeing the sun? The answer may be found not in any single theory, but in the resilience of the human spirit, a spirit that carved hope into solid rock. The Great Wall of China stretches across thousands of miles, yet its most debated section is the Ming dynasty's ambitious project. When the Ming took power in the late 1400s, they inherited a scattered collection of older walls and barriers, but they envisioned something far more unified. Over the next 200 years, they transformed these fragments into a continuous defensive system that still defines how we imagine the wall today. Yet the way they built it remains a puzzle for modern researchers, not because the techniques are unknown, but because the scale is so staggering that it challenges our assumptions about what was possible with medieval resources. One of the deepest debates revolves around logistics. Moving millions of tons of stone, brick, and timber across steep mountains and through arid deserts required an organized effort that would strain modern supply chains. How did Ming officials coordinate the delivery of materials to remote construction sites? Written records from the period mention that local populations were required to contribute labor and materials as a form of tax. Villages near the wall were responsible for producing bricks, burning lime for mortar, and quarrying stone, but the distances involved meant that many materials had to travel dozens of miles over rough terrain. Some historians argue that the Ming built a parallel network of roads and canals specifically for this purpose, a hidden infrastructure that has mostly vanished. Others point to the use of rivers for transport, with bricks and timber floated downstream to collection points. Yet the evidence for these routes is fragmentary, and no complete map of the supply chain survives. The construction techniques themselves are a separate mystery. In the eastern sections near Beijing, the wall is made of brick and stone, laid with a mortar that includes sticky rice, a mixture that gives the joints exceptional durability. Chemical analysis has confirmed that this organic additive helped the mortar resist cracking for centuries. But how did the builders standardize the recipe across hundreds of miles of wall? The ratio of lime to sticky rice had to be precise, and the ingredients had to be consistent. Some researchers believe that the Ming government issued official manuals that specified the exact proportions, and that local supervisors were trained to follow them. Others argue that the knowledge was passed down through generations of master masons, with each region adapting the formula to local materials. The result is a wall that varies in composition from one section to another, yet every part has lasted remarkably well. Further west, where forests were scarce, the wall was built using rammed earth, a technique that layers moist soil and gravel inside wooden forms, then pounds it into a dense, rock-hard mass. This method required no firing and no imported stone, but it demanded an enormous labor force working in precise coordination. Workers had to mix the earth to the right moisture content, tamp it in thin layers, and allow each layer to dry before adding the next. A single section could take months to complete. The mystery here is how the Ming managed to maintain quality control across such a vast territory. Rammed earth walls can crack and erode if the layers are not compacted evenly. Yet large stretches of the Ming Wall in the west still stand, some rising over 30 feet high. modern engineers have tested samples and found that the density rivals that of modern concrete. This suggests that the workers followed a strict protocol, but no detailed description of that protocol has survived in the historical record. The integration of natural barriers adds another layer of complexity. In many places, the wall does not follow a straight line but hugs the crests of cliffs and the edges of deep ravines. The builders used these features as ready-made obstacles, positioning the wall so that attackers would have to climb steep slopes before even reaching the base. This required careful surveying because a wall built too far from a cliff edge would leave a flat approach for enemies, while a wall built too close might collapse into the gorge below. How did Ming surveyors determine the optimal placement? They left no written calculations, only the wall itself as evidence. Some researchers believe they used a simple method of sighting along two fixed points, similar to Roman surveying but adapted for mountainous terrain. Others suggest they used long measuring ropes and plumb lines to map the contours, then built temporary observation towers to check alignment. The exact technique remains speculative. Finally, the maintenance of such a long wall over 2 centuries presents its own mystery. The Ming government established a system of garrison posts along the wall, each responsible for maintaining a specific section. Soldiers were also laborers tasked with repairing cracks, replacing loose bricks, and clearing vegetation. But the wall stretched over 5,000 miles, and the number of soldiers stationed never exceeded a few 100,000. How did they keep the entire structure in working order? Some sections were likely abandoned for years at a time, only to be repaired when a threat emerged. Others were maintained continuously because they guarded critical passes. The debate centers on whether the wall was ever fully manned and maintained simultaneously, or whether it functioned more as a deterrent and a controlled border than an active fortification. The answer probably lies somewhere in between, but without detailed records, we can only guess. What remains certain is that the Ming Great Wall is not a single monument but a patchwork of solutions, each adapted to the local landscape and resources. The builders understood that a wall in the mountains required different materials and methods than a wall in the desert. They also understood that the wall alone could not stop an invasion, but that it could slow an enemy enough to allow reinforcements to arrive. That practical mindset led them to create something that still impresses us with its scale and durability. Yet every time we study a new section, we find new questions. How long did it take to build that particular watchtower? Why did they use brick here and rammed earth a mile away? The wall keeps its secrets, and perhaps that is part of its power. It challenges us to appreciate what can be achieved when human effort is organized toward a single purpose, even when the full story remains out of reach. High in the Andes, another kind of wall puzzles engineers. The Inca fortress of Sacsayhuaman, perched on a hill overlooking the ancient city of Cusco, is built from stones so massive that some weigh over 100 tons. Yet they fit together with a precision that allows no blade of grass to slide between them. The joints are so tight that even a sheet of paper cannot be inserted. These stones were cut and placed without the use of wheels, iron tools, or draft animals. How the Inca achieved this remains one of the most hotly debated questions in archaeology. The stones themselves come from quarries miles away, and some weigh as much as a fully loaded semi-truck. Moving them over rugged Andean terrain, often uphill, would have required ropes, levers, and immense human effort. But the real mystery is not just transportation, it is the shaping and fitting. Many of the stones have 12 or more faces, each cut at a precise angle so that the block locks into its neighbors like a 3-dimensional puzzle. Modern masons who have tried to replicate this using only stone tools have found it nearly impossible to achieve the same consistency. So how did the Inca do it? One theory suggests that they used a technique called stone softening. The idea is that Inca workers applied plant juices or acids to the surface of the stone, making the outer layer temporarily softer and easier to shape. Some researchers point to local plants like the San Pedro cactus or certain vines that produce sap containing mild acids. The theory goes that workers would carve the block roughly at the quarry, then apply the plant mixture to soften the surface, allowing them to scrape away small amounts with harder stones. Once the block dried, it would regain its original hardness. This explanation is appealing because it accounts for the near-seamless fit. But critics note that no archaeological evidence of such acids has been found on the stones themselves, and the time required to soften such massive blocks would have been enormous. Another theory proposes that the Inca used heat to melt the stone surfaces. The idea is that they built large fires against the rock, then quickly doused it with cold water, causing the surface to crack and flake off in thin layers. By repeating this process, they could slowly shape the block to the desired shape. Some supporters of this theory point to the fact that many stones at Sacsayhuamán show signs of thermal fracturing, a pattern consistent with rapid heating and cooling. But melting stone would require temperatures far beyond what a wood fire can produce, and the Inca had no technology to reach such heat. What they might have done is use fire to weaken the stone, then hammer it with harder rocks to knock off unwanted pieces. This is a variation of the third and most widely accepted theory, meticulous hammering. In this view, Inca stoneworkers used hammerstones of a harder rock, such as diorite or quartzite, to pound the surface of the softer andesite or limestone blocks. By striking thousands of times in a controlled pattern, they could gradually shape the stone with incredible accuracy. This technique, known as pecking or hammer dressing, leaves a characteristic dimpled surface that matches what is seen on many Inca stones. The hammerstones themselves have been found at quarry sites worn down from use, but even this theory has its gaps. To produce the flat faces and tight joints found at Sacsayhuamán, workers would have needed to test the fit repeatedly, lifting and lowering the blocks to check the contact points. This process, known as trial fitting, would have required meticulous planning and an enormous amount of lifting. Some researchers suggest that the Inca built temporary ramps of earth and stone to raise the blocks into position, but no remains of such ramps have been found at Sacsayhuamán. Others propose that the blocks were slid into place on a bed of rollers or lubricated with mud, but the steep slopes would have made this extremely dangerous. The mystery deepens when you consider that the entire fortress was built over a period of about 50 years, a relatively short time for such a massive project. If the pecking theory is correct, how many workers would have been needed, and how did they coordinate their efforts without written plans or modern surveying tools? Some archaeologists argue that the Inca used scale models made of clay or stone to plan the layout, and that they passed instructions orally through a system of overseers. But no such models have been found. Every theory has its weaknesses, and the debate continues. What makes Sacsayhuamán so compelling is that the stones themselves resist simple explanation. They stand as a testament to a culture that achieved extraordinary results with limited technology. The questions left unanswered remind us that engineering is not just about tools, but about ingenuity, patience, and a deep understanding of materials. Perhaps the Inca simply had a method that we have not yet reconstructed, a method that vanished with the last master stoneworker. As long as those stones remain in place, they will keep asking us to look closer and wonder. The Leaning Tower of Pisa began tilting before it was even finished. Construction started in the year 1173, but by the time workers reached the third level, the ground beneath the south side had started to sink. The soil there was a mix of clay, sand, and waterlogged silt, a combination that could not support the massive weight of the tower. Medieval engineers faced an impossible choice. They could abandon the project entirely, or they could try to adapt the design to compensate for the lean. They chose the second path, and that decision created one of the most iconic structures in history, as well as an enduring mystery. How did they manage to build a tower that leaned without it toppling over, using only the tools and knowledge of the 12th century? The builders responded by making the upper floors taller on the south side, effectively curving the tower upward in an attempt to bring the vertical axis back toward the center. You can see this correction clearly if you look at the tower from the side. The lower levels lean 5.5 degrees, but the upper floors gradually straighten, so the angle decreases as you go up. This adjustment worked well enough to allow the tower to be completed in the late 1400s, nearly 2 centuries after it began. But the mystery of the original design runs deeper. Was the tower always intended to be slightly tilted? Some architectural historians argue that the original plans may have assumed a certain amount of settlement, and that the builders deliberately built on compressible ground to reduce stress on the foundations. Others point to evidence that the foundation was far shallower than it should have been, only about 10 feet deep, which suggests that the engineers either miscalculated or accepted a known risk. The debate has never been fully resolved because no complete original blueprint survives. What we do know is that the tower kept leaning for centuries, slowly increasing its tilt until it reached about 5.5 degrees by the 20th century. At that point, it was in serious danger of collapse. In 1990, the Italian government closed the tower and launched a major stabilization effort. Engineers studied the soil, the foundation, and the exact geometry of the structure for over a decade. They eventually used a technique called soil extraction, carefully removing small amounts of earth from underneath the north side, allowing the tower to settle back slightly. This reduced the lean by about half a degree, enough to ensure stability for another 200 years. The project revealed surprising secrets. The tower was not solid stone but a hollow cylinder with an inner and outer shell connected by spiral staircases. The weight was distributed unevenly, and the marble facing had cracked in ways that suggested the structure was more flexible than anyone had realized. As engineers worked, they discovered that the tower had been slowly adjusting its own balance over the centuries, like a living thing finding its footing. The medieval builders had not fixed the lean, but they had created a structure resilient enough to survive almost 1,000 years of gradual movement. That resilience is the real mystery. Why did the tower not fall? Modern simulations show that the foundation, though shallow, sits on a layer of dense sand that compresses slowly, acting like a natural shock absorber. The clay below that sand has enough plasticity to redistribute stress without fracturing. The builders could not have known this in detail, but they had centuries of local experience in building on the soft ground of the Po River Delta. They understood that some settlement was inevitable, and they designed the tower with a broad base and a gradual taper that helped spread the load. The tilt itself may have saved the tower by shifting the center of gravity away from the weakest soil and onto firmer ground. The more we study the Leaning Tower, the more we realize that its survival is not just luck, but a testament to a deep, intuitive understanding of how structures interact with the ground. The engineers of the 12th century did not have computer models, but they had generations of trial and error, and they were willing to adapt as the building told them what it needed. The tower still leans today, but it leans with purpose, a living lesson in the art of compromise between human ambition and the stubborn earth beneath our feet. Across the Spanish city of Segovia, a Roman aqueduct still carries water using only perfectly cut granite blocks, no mortar at all. This massive structure, built nearly 2,000 years ago, stretches for over 15 kilometers from the distant mountains into the heart of the city, and its most famous section, a double tier of arches rising 28 meters above the plaza, has become an enduring symbol of Roman engineering. But the real marvel is not the height or the beauty. It is the fact that the entire aqueduct was assembled without a single drop of mortar, relying entirely on the precise fitting of stone against stone. Each granite block was carved so exactly that the joints are nearly invisible, held together by gravity and the immense weight of the structure itself. How did Roman builders achieve such precision over such a long distance? The debate among researchers centers on the surveying methods used to maintain a consistent gradient across miles of uneven terrain. Water must flow downhill, but the slope has to be gentle enough to prevent erosion and fast enough to keep the water moving. The Segovia aqueduct descends at an average gradient of about 1%, a slope so subtle that you would not notice it walking beside the channel. Yet that gradient had to be maintained continuously over hills, valleys, and through the city itself, with no modern levels or laser tools. Some historians argue that the Romans used a device called a corybates, a long wooden ruler with a water channel carved into its top. By filling the channel and sighting along the surface, surveyors could determine whether 2 points were level. But leveling over such a long distance would have required hundreds of setups, each one carrying a tiny error that would accumulate. How did they correct for those errors? No written record explains the exact procedure. Other researchers propose that they used a system of water levels, essentially long hoses or pipes filled with water, which naturally find a level at both ends. This method is simpler and potentially more accurate over long distances, but it requires flexible tubing that could withstand pressure, something not clearly documented for Roman times. A third theory suggests that the builders used a combination of both, plus repeated checks and adjustments as they went. The real genius may have been in the block cutting itself. The granite was quarried from nearby mountains, and the blocks were shaped on site using iron chisels and hammers. Workers carved each block to a specific angle so that it would lock into its neighbors, creating a self-supporting arch that needed no binder. The friction between the stones was enough to hold them in place, even under the constant vibration of flowing water. Over the centuries, the aqueduct has survived earthquakes, wars, and the slow erosion of wind and rain. Sections have been repaired, but the original blocks remain, still fitting together as tightly as the day they were set. The mystery of how Roman surveyors maintained that 1% grade over kilometers of stone and earth is not just an academic question. It speaks to a level of planning and precision that we often associate only with modern infrastructure. When you stand beneath those arches and look up at the stones stacked without mortar, you are looking at centuries of accumulated knowledge, passed down from master to apprentice, tested on 100 projects before this one. The answer may never be fully recovered, but the aqueduct itself is the proof that such skill existed, and that it was good enough to last far beyond the empire that built it. Some of the oldest standing houses in Europe are made entirely of wood and have survived for over 5 centuries. Their frames remain straight, their joints tight, and their walls still shelter families, yet they were built without a single iron nail. Medieval carpenters relied only on wooden pegs and carefully cut joints to hold massive oak beams together for generation after generation. How did they design these structures with such precision using only hand tools and geometric rules passed down by word of mouth? The debate among architectural historians centers on the level of mathematical knowledge these craftsmen possessed. Some scholars argue that carpenters used a kind of practical geometry, taught through pattern books and physical templates, that allowed them to calculate angles and proportions without written formulas. Others point to the existence of simple measuring tools like the square and the compass, combined with a deep understanding of how wood behaves under load. The real mystery emerges when you look at the joints themselves. Mortise and tenon joints, dovetails, and scarf joints lock together so perfectly that they resist both gravity and the slow movement of wood as it dries and swells with the seasons. Modern attempts to replicate these joints using only period tools have shown that even experienced woodworkers struggle to achieve the same consistency. The carpenters of the Middle Ages must have developed a system of markings and layouts that encoded centuries of trial and error into a repeatable process. That system was rarely written down and almost never explained in full. The longevity of these buildings adds another layer to the puzzle. An oak timber frame can last hundreds of years, but only if the joints are tight enough to prevent rot and the beams are properly seasoned. Medieval carpenters understood the properties of different types of wood, when to cut it, how to dry it, and how to orient the grain to minimize warping. They also knew how to design the frame so that it could shift slightly with the ground beneath it, settling over time without pulling apart. Some of these houses have survived earthquakes and floods, standing while newer structures have crumbled around them. The knowledge that made this possible was not considered mysterious by its creators. It was simply the craft of their trade, learned through apprenticeship and refined through practice. But because it was never fully recorded, it has become a puzzle that we are still trying to piece together from the few surviving building accounts and the silent evidence of the structures themselves. Every time we study a medieval timber frame, we are looking into a workshop that vanished centuries ago. The carpenters left behind no theoretical treatises, only the buildings that still shadow our streets and villages. What else did they know about working with wood that we have forgotten? And can we reclaim some of that wisdom before the last of those ancient frames finally gives way to time? These 10 mysteries barely scratch the surface of what we do not know about the past. From Roman concrete that heals its own cracks to Inca stones that fit without a hairline gap, from underground cities ventilated by cunning shafts to timber frames that have outlasted iron nails, each structure challenges our assumption that modern engineering has surpassed everything that came before. The truth is more humbling. Every time a researcher discovers a previously unknown technique, such as the hot mixing of Roman concrete or the use of sticky rice in Ming mortar, we realize how much ancient knowledge was never written down. The loss is not just technical, it is a loss of perspective, of understanding how communities adapted to their local materials, climate, and challenges over centuries of patient trial and error. These structures endured not because their builders had better tools, but because they had deeper observation, passed from master to apprentice across generations. They watched how stone weathered, how wood moved, how water flowed, and they let those observations guide their hands. We may never recover the full toolkit of the medieval carpenter or the Roman surveyor, but the structures themselves remain as teachers. Every time we study a granite block at Segovia or a timber joint in an English barn, we are asking questions that the builders never imagined anyone would ask. Yet the answers are still there, hidden in the patina of age, waiting for the right combination of curiosity and science to bring them to light. So I will leave you with this. Which of these 10 mysteries captured your imagination the most? Was it the self-healing concrete, the leaning tower that refused to fall, or the underground city that could sustain an entire community in darkness? Let me know in the comments below. Your thoughts help shape future explorations, and if you want to continue this journey into the lost knowledge of our ancestors, hit the subscribe button and stay with me for more discoveries that challenge everything you thought you knew about the past.